Now let's talk about calculations of harmonic frequencies. Now, the thing we need to be clear is, okay, now the certain frequency on a string that causing first harmonics is really depends on the length between A and B. Okay, so just let's make it clear. Okay, the length in meters between the two ending points, they're important. Okay, and if you have a look at this graph, okay, if you have a look at this graph, okay, it is a half of a wave. Okay, this graph, if let me just dot it. Okay, this part of the graph on the top is basically half of the wave. Okay, so the wavelength of the standing wave, okay, the wavelength of the first harmonic, okay, is basically 2 times the length between AB. Okay, 2 times the length between AB. Okay. Then, using our wave equations, okay, remember our velocity of the wave is frequency times wavelength. Okay, since the frequency is basically velocity divided by the wavelength. Okay, since the wavelength is 2 of the length, so frequency will be velocity of the wave, the speed of the wave, divided by 2 times L. Okay. Now, if we try to do the similar thing, okay, L still be the length, and the wavelength in this case, okay, is same. Say this is a complete period, complete cycle of a period. Okay, so the wavelength is same as L. Okay, using the equation, frequency is velocity divided by the wavelength. Substituted, we have this. Okay. Now, if we look at the third harmonic or the second overtone, okay, that's lambda 1, lambda 2, lambda 3. What can we say is now we have one period, one wavelength of the one wavelength is actually 2/3 of the whole length. Okay. So, yep. So 2/3 of the whole length is our wavelength. Using the equation to find in the particular frequency that can produce third harmonic will be V equal to divided by the wavelength, which is 3V divided by 2L. Okay. But now, just remember that the scientists normally sometimes dealing with the 10th harmonic or the 11th harmonic or the 12th or the 100th harmonic. Okay. If we do that all the time, it would be just annoying. So what they came up is they came up with a formula. Okay. So I have, look at this one, I have V divided by 2L, okay, for first harmonic, okay, V divided by L for second harmonics, or 2V divided by 2L. If I just change the equation, makes the denominator the same. So then I have 3V divided by 2L. Okay. So the scientists have an equation which is on your D7 notes, page 8.6. Okay. What they do is, okay, the wavelength is basically 2L divided by N. Okay. 2L divided by N. Okay. And N is the number of harmonics. N would be equivalent to, N is let me write it down here. N is basically 0, 1, 2, 3, etc. Okay. And the velocity, the frequency, okay, let me rewrite it, is practically N times V divided by 2L. Okay, so this is the formula you're going to use, okay, for standing waves when both ends are fixed. Okay, this is really important. Okay. Okay. For both ends, for both fixed ends. Yep. And for instance, when we're looking at the first harmonic or the fundamental frequency, yeah, n equals to 1. Okay, we have n equal to 1, we label it lambda 1. Okay. For the second one, n is 2, we label it, yep, n will be 2. Okay. Just remember, second harmonic, first overtone, n is 2. Then we have the third harmonic, second overtone, n equals to 3. Lambda 2 and lambda 3. They all phase with these formulas. Okay. So here, yep. So those are the basic calculation of it.